Alright, today we will talk about the chain rule, which you've met informally already in some previous videos and in some of the exercises from the book. Our goal for the day will mostly be speeding up the process. But first, let me remind you of how it works. We use the chain rule to take derivatives of compositions of functions. If we start with some function f, and we consider its output f of x, and then run that whole expression through another function, g, so that we end up with g of f of x, the chain rule will tell us how to find the derivative of that composition of functions. And in situations like this, it's often helpful to think of this function as the inner function, and this one as the outer function. For a specific example, let's consider the composite function sine of 3x squared plus 5. Now the way this composite function works is that you start with an input, x, and you apply two steps to it. First, you apply this quadratic function to it, 3x squared plus 5. That is our inner function. And once you've applied this quadratic, then you take the result and hit that with the sine function, which is our outer function. Now, if our problem is to find the derivative of this composite function with respect to x, how are we going to do that? Well, recall the idea from the earlier videos or homework problems from the book. We can introduce a new variable. We can make a substitution that will act as a stepping stone between x and y. What we'll do is we will rewrite this function, y equals sine 3x squared plus 5, by replacing the inner function by a new variable, which we will call u. And of course, we have to explain exactly what u is, so I'll write here, where u is 3x squared plus 5. So essentially, I have taken this composition and broken it into two stages, corresponding to the inner and outer functions. Instead of writing y directly as a function of x, we're writing y as a function of u, which itself is a function of x. We can visualize this as a chain of three variables, hence our chain rule. Our goal is to find dy dx, the derivative of the top variable with respect to this bottom variable. And our strategy will be to use u as a stepping stone, to go from y to u and then u to x. So coming back over here, now that I have written y in this way, I can start to think about dy dx. And what I can do is to factor dy dx into a product of two derivatives, namely as dy du times du dx. And of course this equal sign holds because those du's just cancel. This expression right here, that factorization of dy dx, really is the statement of the chain rule in Leibniz notation. Nothing could be simpler. It's a little trickier to express in prime notation, but we will want to do that for our speeded up version of the chain rule. But before we get to the speeded up version, let's just continue on and see how this works. Our first factor here is dy du, the derivative of y with respect to u. Well, we know what y is as a function of u. Y is sine of u. Therefore, we know what the derivative of y with respect to u is. It's going to be cosine of u. And we're going to have to multiply that by the derivative of u with respect to x. Well, to find that derivative, we need u as a function of x. We have that right here in our little dictionary. Derivative of u with respect to x is going to be 6x. And now we're practically done, apart from cleaning this up. We need to rewrite it so that it's a function of x. We don't want this intermediary u still to remain. How do we do that? Well, of course, we just use our dictionary entry. We can translate u to 3x squared plus 5. So we can rewrite that first factor as cosine of 3x squared plus 5. And of course, the 6x just comes along for the ride, and we would normally clean this up and write it with the usual stylistic conventions so that this would be 6x times cosine 3x squared plus 5. And we're done. Easy enough. Let's do another example over here. We want to find dy dx if y is the quantity x cubed plus 2x raised to the 50th power. Now there's a very nasty way to do this, which would be to actually expand this out, which would take you quite some time, but you could do it, and then once you had it, you would have a gigantic polynomial, a 150th degree polynomial in fact, and then you could take its derivative in the usual way. But there's a much nicer way to do it, which is just to use the chain rule, which you can do once you recognize that this is not just a polynomial, but a composition of functions. The inner function here is this cubic polynomial, x cubed plus 2x, while our outer function is this power function that takes its input and raises it to the 50th power. So in sum, we could rewrite this expression, y equals x cubed plus 2x to the 50th, by introducing our stepping stone u, so that it now looks like u to the 50th, where u is x cubed plus 2x. And now that we've done this, written y as a function of u, which itself is a function of x, we can find dy dx. We factor this into a product of two derivatives, dy du times du dx, and we compute each derivative separately. Derivative of y with respect to u. Well, we need to think what y is as a function of u. It's u to the 50th. That means derivative of y with respect to u is 50 times u to the 49th. The second factor is du dx. Well, to find that, we need u as a function of x, which we have right here. U is x cubed plus 2x, so the derivative of u with respect to x is going to be 3x squared plus 2. And now all we have to do is write this all in terms of x. The only thing we have to take care of is translating u into the language of x, which we can do with that dictionary entry right there. So that instead of having 50 times u to the 49th power, that first factor will now become 50 times x cubed plus 2x to the 49th power times 3x squared plus 2. And if this was the full extent of the problem, well, I would take off those brackets because they're not doing any work here and call it a day. But I'm going to leave them on just because they're going to help me emphasize something that this chain rule problem had in common with this chain rule problem. In fact, to discuss the similarities, I'm going to go ahead and get rid of that last step, even though that's the nice, clean version of how you would actually write it in practice. Okay, now these look superficially similar. In both cases, the stuff in brackets corresponds to dy du, and the stuff at the end corresponds to du dx. I'm going to get rid of this stuff too, which is getting in the way. And I want to emphasize one other feature that we see inside the brackets in both cases. Let me do a little color coding. That's better. The stuff I've put in red down here, x cubed plus 2x, is the original inner function in our composition of functions. Of course, we're not surprised to see the inner function show up at the end, because the last thing we did in both of these problems was to substitute the inner function back in for u. We see the same thing over here. 3x squared plus 5 was the inner function. Of course it shows up, because the last thing we did was to substitute that in for u. This was dy du, and then we rewrote it in terms of x. This was dy du, and then we rewrote that in terms of x. Anyway, let's see if we can describe, just in words, what this stuff in the brackets, what the first factor in both cases represents. Well, it was dy du, which is the derivative of the outer function, because we're taking the derivative of y, the outermost function. Maybe I needed my little ux thing in there after all. dy du is the derivative of y with respect to u. So this is the derivative of the outer function, but we don't leave it in terms of u. We substitute the inner function in for u. So in other words, it's the derivative of the outer function evaluated at the inner function. Because to evaluate a function just means to stick something in. So the outer function was sine, the derivative of the outer function is cosine, and then we evaluated that cosine at the inner function. Similarly over here, the outer function was whatever to the 50th power, like u to the 50th. The derivative of the outer function is 50 times whatever to the 49th power, and then we evaluated that thing at the inner function, x squared plus 2x. We put that in where we would have our whatever, our u. So summing these up, we can see that the pattern we obtain in the chain rule looks something like this. This first factor, the dy du factor, it's the derivative of the outer function evaluated at the inner function. Again, to connect that with this basic factorization, it's the derivative of the outer because we're taking dy du, the derivative of this outermost function. It's evaluated at the inner function because we're putting it back in terms of x, which comes down to just eliminating the u. Same story over here. This first factor is the derivative of the outer function. The outer function is u to the 50th, or whatever to the 50th, so that we get 50 times whatever to the 49th. But then we had this second step as well, which is where we took the derivative of the outer and evaluated it at the inner function. This might seem tedious for me to spell this all out, but it really will make it easier for you to apply the chain rule quickly in the future, because what we'll be doing is, instead of explicitly writing this with a u in it, and explicitly factoring it out, and explicitly writing down each derivative, and so on and so forth, we'll just think in our minds, oh, it's a chain rule. That's derivative of the outer evaluated at the inner times some other factor. Well, what's that other factor? That's the easy part. The 6x here, for example, was the du dx. This 3x squared plus 2 over here was the du dx. No matter what we had, no matter what composition of functions, that second factor is just du dx. We're just taking that inner function, that u, and taking its derivative with respect to x. So we can just say straight out that the second factor, du dx, that just corresponds to the derivative of the inner function. What we have done is we've taken this very clean statement in Leibniz notation, this factorization of a derivative, which is completely obvious, and we have rewritten it in this rhetorical form. So let me go ahead and write down the chain rule in its rhetorical version. Take the outer function's derivative, evaluate it at the inner function, and then multiply by the inner function's derivative. I need some room, so I'm going to box this up and clear out all this other stuff and move this up top. Okay, and there it is. Each line I have written down here just corresponds to one of those two factors. Outer function's derivative evaluated at the inner function, that is just dy du. Multiply by the inner function's derivative, that is just du dx. And the way we use the chain rule in practice is to just think through this rhetorical version without bothering to write down u explicitly. Let's go back to one of the examples we just did, for example. If y is sine of 3x squared plus 5, then what is the derivative of y with respect to x? Well, we just saw how we could do this with the chain rule by making this very explicit, writing it as sine of u, where u is 3x squared plus 5, and then factor this as dy du, du dx, etc., etc. But I claim that with this rhetorical version of the chain rule, we can do it all in one shot. So let's get rid of this question mark. We just have to remember what the chain rule says rhetorically. Outer function's derivative, evaluated at the inner, multiplied by the inner function's derivative. Now we just have to identify the inner and outer functions. Well, that's easy. The inner function is this quadratic, and the outer function is sine. So let's get to work. Take the outer function's derivative and evaluate it at the inner function. The outer function is sine, so its derivative is cosine of something. Of what, though? Well, we're evaluating it at the inner function, so what goes in here is the inner function itself. 3x squared plus 5. And this is the first of our two factors, corresponding to the two lines here. We have to multiply it by the inner function's derivative. Well, here's the inner function, 3x squared plus 5. So its derivative is 6x. And that's it, apart from cleaning this up, which just means writing it as 6x times cosine 3x squared plus 5. And we're done. So that first equal sign is justified by the chain rule in its rhetorical form. And notice how much shorter this is than what we did before. We're doing the exact same thing. We were still finding dy dx by getting dy du and then multiplying by du dx. That's what those two factors are. But we've speeded the process up by thinking about it in this form. Let's do another example of the chain rule in this sped up rhetorical version. Let's look at y equals e to the 3x. Now this is very compact, but it's still a composition of functions. The inner function, the first thing you apply to x, is this simple linear function, the tripling function. You take the output of that tripling function and apply the exponential function to it. If we were going to write this out in gory detail, we would say that this is e to the u, where u is 3x. Here's the inner function, and the outer function is just the exponential function e to the u. But I'm not going to go through all the gory details. I recognize it's a composition of functions, and therefore I can take its derivative using the chain rule. What's its derivative going to be? Well, the first factor is outer function's derivative evaluated at the inner function. Well, the outer function is the exponential, e to the whatever, or e to the u. The derivative of e to the whatever is e to the whatever. So I'm going to get e to the something. I'm evaluating it at the inner function, which is 3x. So that 3x is going to go in there and give me e to the 3x. But I am not done. That is just the first factor. That's the derivative of the outer function evaluated at the inner. But I have to follow the chain on down. I have to take the derivative of the inner function. Well, the inner function is 3x. Its derivative is just 3. Don't forget that 3. And then at the end, rewrite this in the usual way so that people don't think you are ill-bred. That should be 3e to the 3x. And that's it. Notice how quick that was. And again, that first equal sign is justified by the chain rule, even though we haven't written out an explicit intermediate variable u. By the way, notice how this rhetorical statement of the chain rule is kind of mysterious. It's something you just have to learn and get used to it, whereas the statement in Leibniz notation is completely obvious. It's just a matter of multiplying two fractions. That's one of the advantages infinitesimals give you. It lets you see the things that are obvious underneath the things that may look like they are somewhat arbitrary. They're not arbitrary. Everything you learn in calculus happens for a specific reason. Anyway, let's do another example. Let's say y is the square root of 5x plus 9. This is obviously a composition of functions. We have an inner function, a linear function of 5x plus 9, and then we take the result of that and take its square root. So the square root function is our outer function here. We want to know what the derivative is here. And since this rhetorical statement doesn't make any specific reference to notation, I can certainly use prime notation here if I want to. So what's y prime? What's the derivative of this composition? Well, we take the outer function's derivative and evaluate it at the inner function. The outer function here is the square root function, and as we discussed in an earlier video, and which hopefully you have well memorized by now, the derivative of the square root function is 1 over 2 times the square root of, well, whatever the relevant variable is. But what is the whatever? Well, we are evaluating at the inner function, and the inner function here is 5x plus 9, so that's what goes in there, and we end up with this. But we are not done. That was only the first step. We have to continue the chain. We have to then multiply by the inner function's derivative. Well, the inner function is 5x plus 9, so that means I have to multiply all this stuff by 5, since that's the derivative of 5x plus 9. And we are done, apart from cleaning this up, of course, which we can do just by sticking the 5 back up here. Good. As you can see, the chain rule is easy once you get used to it. And the only way to get used to it is by doing lots of examples. Only you can do that. You can watch me do it all day long, and it's not going to help you that much. You have to sit down and do several dozen of these. I've noticed that one thing that really makes the chain rule click into place for some students is by seeing it in an example where you have a pretty long chain. Not just 2 functions, but maybe functions nested 3 or 4 deep, or even more. Let's do an example like that now. Let's look at y is sine of cosine of x squared. Okay, cosine of x squared is our inner function, and sine is our outer function. Well, that's fine, but notice that our inner function itself is a composition of functions. It's made up of an inner function, if you like, x squared, and I guess you could call it an outer inner function, cosine. But the nomenclature doesn't matter. We can still just do the chain rule. It's just that our chain is a little longer. We always start with the outermost function and work our way to the inside. Let's see how it works. We're going to start with our outermost function, sine, because we're thinking of that as the outer function and everything left inside as the inner function, even though the inner function is complicated in this case. Start with the outermost function, sine. We're going to take its derivative and evaluate at the inner function. Well, the derivative of the outermost function is, of course, cosine, and we have to evaluate that at the inner function, which is cosine of x squared. But we're not done. That's just that first line. We still have to multiply by the inner function's derivative. So that we don't get lost, let's notate this carefully. We're taking all this stuff and multiplying it by the inner function's derivative. Well, let's continue onwards. Bring all this stuff down, and now let's actually take this derivative. Using the chain rule, of course, because this is a composite function. How do I do the chain rule? Same old story as always. Derivative of the outer evaluated at the inner times the derivative of the inner. Well, what's the outermost function here? It's cosine, and the derivative of cosine is minus sine. Of what? Well, I'm evaluating at the inner function, which is x squared. But I'm not done. This is just the first step of this application of the chain rule. I still have another factor. I have to multiply by the inner function's derivative, the inner function in this little piece. Well, that's the derivative of x squared, so I'm going to get 2x. And now I'm done. I've reached the end of the chain. There are no more derivatives to take, whereas up here I still had one to go. So I can just combine all that stuff into one piece and write it as something like that. And we're done. After a while of doing problems like this, you will probably be comfortable going from the function straight to a step like this without even having to write down this intermediate derivative. But in the beginning, do it. Do it every time, and do it on your tests so that I know that you know what you are doing. Because if you make a big leap and you land in the wrong place and there are no intermediate steps, well, who knows what happened. And since when you're taking a test, your job is to show me what happened, I won't be able to give you much partial credit. Let's do another example. Let us consider this function. Y is the square root of the logarithm of x to the 4th plus 1. Like the previous one, this is nested 3 deep. The innermost function is this 4th degree polynomial, then we take a logarithm, and then finally we apply a square root. But all that matters to me is that I can identify the outermost function, the square root, and then the rest I can just call the inner function. To find the derivative of y, we take the derivative of the outer function. Well, that's the derivative of the square root function. And as we saw in an earlier example, that's 1 over 2 times the square root of something. But what's the something going to be? Well, we are evaluating at the inner function, which is all this junk. So that gets imported into that, and we end up with 1 over 2 times the square root of log x to the 4th plus 1. But we are not done. This is just the first line here. This is the derivative of the outer function evaluated at the inner function. We still have to take the derivative of the inner function. So we carry everything down and just concentrate on this new piece, the derivative of log x to the 4th plus 1. Well, to take that derivative, we need the chain rule because that's a composite function. Outermost function, logarithm. But what's the derivative of the natural logarithm? We have said it's the reciprocal function. So it's 1 over, what am I evaluating at? I'm evaluating at the inner function, which is x to the 4th plus 1. So that is what I get there. But I am not done. I still have to multiply by the inner function's derivative, as I'm taking the derivative of this composite function. That means I have to multiply this by the derivative of x to the 4th plus 1, which is, of course, 4x cubed. Combining this all into one fraction, we'll clean it up a little bit, and I even get a little bit of cancellation so that I end up with this. And we're done. We have found the derivative of this nasty function. Let's do one more where the functions are nested 4 deep. Let's find the derivative of f of x, where f of x is 2 raised to the power of arctangent of the square root of the sine of x. How will we solve this? With the chain rule, of course, because this is a composition of functions. I'm going to try a little color coding. Maybe this will help keep everything organized. I am going to write the stuff whose derivative we still haven't taken in green. So I'll begin by saying that f prime of x is the derivative of all of this stuff, the original function. Okay, we need the chain rule. What's the outermost function here? That is an exponential function, 2 to the whatever, or 2 to the u. And all of this stuff combined is our inner function. Well, the first step of the chain rule is to take the outer function's derivative and evaluate it at the inner function. Well, the outer function's derivative, 2 to the u, is something we studied in the previous video. It's an exponential function, and all exponential functions' derivatives are proportional to themselves, where the constant of proportionality is the logarithm of the base. So the derivative of 2 to the u is log of 2 times 2 to the whatever. But we still need to say what goes in this box. Well, this is the derivative of the outer function, and we're evaluating it at the inner function. So everything in there goes straight in there, and we will end up with something like this. But I'm not done. I've only done the first step. This is the derivative of the outer function evaluated at the inner function. I still have to multiply by the inner function's derivative. So let me bring that down here, and there it is. I've kept it in green because I still haven't taken its derivative. We have to continue the chain. So to continue onwards, all the black stuff has already been cooked, so it can just come down. And now we need to tend to this derivative. Of course, I'm going to use the chain rule again, because this is a composition of functions. The outermost function is arctangent, and all of this stuff is the inside function. So the chain rule tells me derivative of the outer, evaluated at the inner, and then multiply by the derivative of the inner. Well, the derivative of the outer function, derivative of arctangent of whatever, or derivative of arctangent of u, is one you should have memorized by now. It's 1 over 1 plus u squared. So the first factor I get here is going to be 1 over 1 plus something squared. But what is that something? Well, this is the derivative of the outermost function here, and I have to evaluate it at the inner function, which is all this stuff. So popping a square root of sine x in there, when I square it, the radical comes off, and we're left with just sine x. But I am not done. I'm taking this derivative using the chain rule. This is just the first of the 2 factors I should get. The second factor is the inner function's derivative. Well, the inner function was the square root of sine x. So I'm going to get this extra factor here like this, the derivative of the square root of sine x. And I've left this in green because it hasn't been cooked yet. I haven't taken its derivative. I have no idea what metaphor I'm making here. What is green before you cook it and black afterwards? Never mind, let's continue onwards. So once again, we'll take all this stuff and bring it down. And now we need to take this derivative. Once again, we are going to use the chain rule, because the thing I'm trying to take a derivative of is itself a composition of functions, with the inner function sine x and the outer function the square root function. By now you know the drill. Derivative of the outer, evaluated at the inner, multiplied by the derivative of the inner. So what's the derivative of the square root function? Well, as we've seen a couple times already in this episode, that is 1 over 2 times the square root of u, of whatever that inner function is. We have to evaluate at the inner function. What's the inner function here? It's sine x, so sine x goes in there. But again, we are not done. This is only the first of the 2 factors that the chain rule is going to give us. The second factor is the derivative of the inner function, the derivative of sine x. But of course, we all know what that is, the cosine of x. And with that, we are done. There are no more derivatives to take. Could you clean this up a little? Not much. You could put it all in one fraction, but that's about the extent of it. So I'm not going to bother. The point of this example, after all, was to practice the chain rule and see it in action again and again and again. I hope the color coding helped a bit. Either way, you've seen a lot of examples by now, and you will have to supplement this with doing many examples on your own, and you can find lots of them in the book. I want to return to our statement of the chain rule, though. Over the course of this video, we've gotten used to using it in this rhetorical form, but remember where that came from. We extracted this rhetorical form from something more fundamental, the chain rule in its Leibniz version, which is a completely obvious thing and merely states that dy dx can be written as dy du times du dx. And the proof of this statement is completely obvious. A second grader could understand it. You just multiply these fractions, cancel the du's, and you get that side. So out of this utter triviality, we have extracted this version of the chain rule, which is really just taking this and restating it in ordinary language, because that's the way we think about it when we're carrying the chain rule out. But what if we wanted to express the chain rule in prime notation? What would that look like? While it may not be clear how to translate from the Leibniz notation version of the chain rule to the prime version, it's easy to translate from the rhetorical version to the prime version. After all, we apply the chain rule to compositions of functions. So if we wanted an expression for the chain rule in prime notation, we would just have to think about what that looks like. A composition of functions is when we start with some function of x, and we then apply another function to the output. And the chain rule tells us how to find the derivative of that composition. That's easy to determine from our rhetorical version, because this expression right here I have clearly labeled f is my inner function and g is my outer function. So I want the derivative of the outer function, g prime, evaluated at the inner function. So g prime of f of x. But I'm not done. I need that second factor, the inner function's derivative. And since the inner function is f of x, the second factor will obviously be f prime of x. And we're done. That is the expression of the chain rule in prime notation. I wanted to show you the chain rule in this prime notation form because that's the way it's often presented initially in textbooks. That was certainly the way I first met it when I took calculus back before the flood. But if you first encounter it this way, it looks very mysterious. It's not at all clear why it should hold. And if you start here and try to prove it directly, you end up with a pretty unilluminating proof. Look in most other textbooks and you'll see what I mean. But what I hope you have seen is that this statement now makes perfect sense because it follows from this rhetorical version. And while the rhetorical version itself might look mysterious, you should be able to recognize that this is just a statement spelled out in English of what this Leibniz version of the chain rule is telling us. And the Leibniz version is something that can be understood in second grade, or whatever grade you learn about fractions in. There are often very, very simple ideas lurking behind things that look complicated. You want to seek those ideas when you are studying mathematics. Yes, by all means, pound out a million problems just to make sure you get the algorithms down, but make sure you understand the ideas. This is a great example of how infinitesimal thinking gives you crystal clear insight into something that looks mysterious otherwise. Okay, some good news. We are now at the end of chapter 2 of the book, and you have reached the point that you should be able to take the derivative of pretty much any function someone can throw at you. Between the derivatives of individual functions that you've learned and the various structural theorems, chain rule, product rule, quotient rule, linearity properties, you should be able to pull apart anything with enough patience. There may be a lot of steps, but each individual step should be very easy. Let me give you one example that uses several rules at once. Consider this function, sine of 5x squared over x log x. Suppose we want to take its derivative. Well, the first thing we might ask ourselves is there any way I can simplify this thing before I start pounding away? No, it doesn't look like it. Very well, then where do we start? Well, this is crying out for the quotient rule, because we're trying to take the derivative of a quotient of two functions. You know the dopey little song, low d high minus high d low over the square of what's below. That is what the quotient rule gives us. Note that I haven't taken these derivatives yet. Don't try to do too much at once, because each one of these derivatives is a bit involved in and of itself. This one, for example, is going to involve the chain rule, because I have a composition of functions there. This one is going to involve the product rule, because I have a product of functions. So let's continue onwards. Bringing some of this stuff down, I'm still confronted with this derivative, which, as we've said, is going to require the chain rule. Well, inner function is 5x squared, outer function is sine. So the chain rule tells me that this derivative is going to be derivative of the outer, which is going to give me cosine, evaluated at the inner, so cosine of 5x squared, times the derivative of the inner, which is, of course, 10x. And that takes care of that derivative. Now we can come over to this second term. This piece just comes down, and now I have to take the derivative of x log x, which is a job for the product rule. And according to the product rule, this is going to be the derivative of the first function times the second function. But the derivative of the first function is just 1. So my first term is going to be 1 times log x, or better known as log x. And according to the product rule, I have to add that to the first function itself times the derivative of the second function. Well, the derivative of log x is 1 over x. So this second term is going to be x times 1 over x, which is better known as 1. And so we are done taking that derivative. And this equal sign is justified by the chain rule over here and the product rule over here. And we are essentially done. Can we clean this up a little bit? Not a whole lot. Pretty much all we could do is combine these two x's here and maybe put the 10 out in front as we usually would to write it like this. And that is the whole thing. This ugly mess is the derivative of this ugly function. And I hope you can recognize that even though the function and its derivative are both ugly, the process by which we took the derivative was completely mechanical. Just the application of some basic structural rules combined with knowledge of derivatives of specific functions, like sine and logarithm and 5x squared and so on and so forth. We have covered a lot of ground in this chapter. When we started the book, at the beginning of chapter 1, you didn't even know what a derivative was. By the end of chapter 1, you knew what derivatives were, and you were able to take derivatives of the simplest functions, polynomials. By the end of this second chapter, which focused on expanding your repertoire of derivatives, you've now reached the point at which you could take the derivative of pretty much any function you are likely to encounter, and all combinations of those functions you're likely to encounter. We truly have developed a calculus of infinitesimals to do this. It becomes almost mechanical. We'll be moving next into chapter 3, where we will start to apply this stuff in a variety of situations. Before we proceed into that chapter, you need to be sure that you really have mastered the techniques from this present chapter, so that when you're solving problems using calculus, instead of just grinding out derivatives, you won't get bogged down by computational details, and you'll be able to concentrate on the ideas involved. Anyway, that is to come. Congratulations on reaching the end of chapter 2, and I will see you next time when we commence chapter 3. So long.